Welcome. I am Dr. Pauline Fu. In this video, I will present binomial probability distribution. Learning objectives. Determine whether a probability experiment is a binomial experiment. Compute probabilities of a binomial experiment. Calculate the mean and standard deviation of a binomial random variable. Finally, graph a binomial probability distribution. To satisfy the binomial BI English word, there are two outcomes. If an experiment has two outcomes, for example, if you flip a coin, you have either head or tail. That is two outcomes. Okay. An experiment is said to be a binomial. You have to satisfy the following conditions. One, the experiment is performed a fixed number of times. Each repetition of the experiment is called a trial. Two, the trials are independent. For example, if you flip a coin, the tail and the head will independent. This means the outcome of one trial will not affect the outcome of another trial. Number three, for each trial, there are two mutually exclusive outcomes, success or failure. For example, if you flip a coin, if you call the head is a success, the tail is the failure. Number four, the probability of success is fixed for each trial of the experiment. Notation used in binomial probability distribution. We use letter N represent independent trials of the experiment. And we use letter P represent the probability of success. And then 1 minus P is the probability of failure. And we use X represent binomial random variable. That denotes the number of successes in N independent trials of the experiment. X is always smaller equal to N. Now let's take a look at an example. The question is, which of the following are binomial experiments? Question A, a player rolls a pair of fair die 10 times. The number X of sevens rolled is recorded. So you roll a die 10 times, and how many sevens you get, you recorded this number. Is this experiment binomial? The answer is yes. Okay. The outcome has two. You either see 7 or you don't see 7. Two outcomes. Okay. And those, you throw it 10 times, each time it is independent. Okay. This question B, the 11 largest airlines had an on-time percentage of 84.7% in November 2001, according to the Air Travel Consumer Report. In order to assess reasons for delays, an official with the FAA randomly selects flights until she found 10 that were not on time. The number of flights X that need to be selected is recorded. Okay. The question asks you, is this the binomial experiment? The answer is no, because it violates fixed number of trials. Okay, fixed number of trials. Next one, there's a mosquito. Which of the following are binomial experiments? Question C. In a class of 30 students, 55% are female. The instructor randomly selected 4 students. The number X of females selected is recorded. So, is this binomial? The answer is no, because it violates the independent trials. The trials are not independent. Take a look at this example. Constructing binomial probability distribution. According to air travel consumer report, that 11 largest air carriers had an on-time percentage of 79% in May 2008. Suppose that 4 flights are randomly selected from May 2008, and the number of on-time flights X is recorded. The question asks you to construct a probability distribution for the random variable X using a tree diagram. So the question is, you select 4 flights, okay? And the number of on-time flights is X. Okay. So this is the using a tree diagram. Let me see. So we use letter S represent success. Use letter F represent failure. So success means on time in this situation. Failure means not on time. Okay. So the first flight, because you select 4 flights. Okay, you select 4 flights. Let's say the first flight is on time success. The second flight could be success, could be failure. Okay, and when the first one, when the first one is success, the second one is success, the third one could be success, could be failure. And when the first one success, second one success, third one is success, the fourth one could be success, could be failure. Okay, so you keep on this pattern. And this is the first flight is success. How about the first flight is failure? You get this tree diagram. And this diagram is the total outcomes for 4 flights. You choose 4 flights. Okay, choose 4 flights. The outcome either SSSS, SSSF, SSFS, until FFFF. Those are all possible outcomes. So this is the tree diagram. And if the question asks you to compute the probability of x equal to 0, x is 0. They actually use, so in this, they actually use S represent success. Okay. So number of successes. This is random variable x, number of successes. Okay. So S is success. Yes, we know that. So this random variable represents number of success x. The question is, what is the probability of 0 success? When you choose 4 flights, none of them are online, on time. So it is this situation here. Did you see here? If you have F, that is a 0 success. Okay, so the probability of 0 here. Okay. And the probability of 0, it is said the probability of on time is 79. So that means not on time is 1 minus 79. 79% is on time. Not on time is 21%. Not on time is 21%. Okay. So the probability of 0 is here. See, F, see here. F. So what is the probability of F? So the first is not on time. The second flight not on time. The third flight is not on time. The fourth flight is not on time. So final result 0.00194. Okay. The same situation, but a different question. The question asks you to compute the probability of x equal to 1. The probability of x equal to 1. Remember what is x? X represents number of success. Okay. And from this tree diagram, you identify those are the outcomes. X equal to 1, those situation. Okay. For this one here, it is SFF. Okay. So SFF. Okay. And this number 1 represents FSFF. It is here. Okay. And similarly, this number 1, okay, coming from here, it is FFSF. Okay. And the last one, this number here, okay, it is FFFS. Okay, so you do multiplication, then add them together. That is the probability of 1. Okay, number of success, x equal to 1. So now, by the same token, compute the probability of x equal to 2. Okay, so those are the situation, the red box, x equal to 2. Okay, and then you take correspondence, those numbers, okay, S or F. And when you say S, when you see S equal to 0.79, the probability of S, okay, probability of S 0.79, okay, and the probability of F 0.21. Okay. So final result, you get 0.16514. This one exactly similar to this one here. So you keep on going, compute the probability of X equal to 3. So those are X equal to 3. Then you look into the corresponding S or F, and you get this result. All right. So can keep on going. The probability of X equal to 4. Okay. So after all of this calculation, you get this table. You get this table. The probability of from 0 to 1, 2, 3, 4. And this is the binomial probability distribution. Generally speaking, the probability of obtaining X successes in n independent trials of a binomial experiment is given by this formula. The probability of X equal to Cnx, okay, you choose X object. Choose X object from the n, remember C represents combination, times P, the probability of success raised to power X, times 1 minus P. 1 minus P is the probability of failure raised to power n minus X. And P is the probability of success. Okay. So this is the binomial formula. Okay. Just let's review commonly used mathematical symbol. If you have at least, no less than, use this symbol. Greater equal to is at least, no more, no less than. And if you have, they are the same as greater or equal to. So these three phrases refer to the same thing. At least, no less than, greater than or equal to. Okay. And then if you have more than, greater than, it is this symbol here. More than, greater than. Okay. Similarly, you have a fewer than or less than. This is fewer than or less than. Okay. And lastly, you have no more than, at most, less than or equal to. You use this one here. So that is the math symbol for some commonly used phrase. So now let's look at this example. Use binomial probability distribution function. According to the experience automotive, 35% of all car-owning households have 3 or more cars. Question A, in a randomly select 20 car-owning households, what is the probability that exactly 5 have 3 or more cars? this n is, this 20 is n, okay, and this number 5 is x, and you plug in the formula. N equal to 20, x equal to 5, and p is the probability of owning 35% is p, okay, probability of having 3 or more cars. So plug in the formula and you get this result. So let's use Excel to verify this result. So in Excel, you use COMBIN to calculate combination. Okay. You have 20 number, select 5. So that is a C combination. And times 0.35 raised to power 5 times bracket 1 minus 0.35 raised to power 20 minus 5. Okay, that is the Excel to calculate. If I press enter, I get this number. Okay, so I just want to copy this formula. Okay. So you can use Excel to do the calculation. Question B. In a random sample of 20 car-owning households, what is the probability that less than 4 have 3 or more cars? Less than 4. The probability of less than 4 is the same as probability of smaller equal to 3. Why? Because this is a discrete probability distribution. Discrete means x can only be 0, 1, 2, 3, 4, etc. X cannot be 3.5, 4.3, okay? So x smaller than 3 is the same as smaller equal to 3. Oh, sorry, smaller than 4 is the same as smaller equal to 3. Smaller equal to 3 means P0 plus P1 plus P2 plus P3. Okay. So what is P0? You use this formula here. P0 means x equal to 0, n equal to 20. Okay. You get this calculation. Question C, same situation. Okay. In a random sample of 20 car-owning households, what is the probability that at least 4 have 3 or more cars? 4 households have 3 or more cars, at least. At least means the probability of greater equal to 4. And then we can use complement event, greater equal to 4. The complement event is smaller equal to 3. Okay, the complement event, remember they're opposite to each other. So greater equal to 4, the probability of greater equal to 4 equal to 1 minus the probability of smaller equal to 3. Okay, and smaller equal to 3, we get the result here. What is smaller equal to 3? 0.0444. And you plug in this number here, smaller equal to 3. Okay. So that is the binomial probability distribution function, okay, to calculate the probability for a binomial experiment. Next, let's calculate the mean or expected value and the standard deviation of a binomial random variable. The formula for the mean is use number of trials n times p. P represents the probability of success. That is the mu, mean. And standard deviation, you use this formula, okay, n times p times 1 minus p, and take square root. Example, okay. According to the Exploring Automotive, 35% of all cars owned in households have 3 or more cars. In a random sample of 400 car owned in households, determine the mean and standard deviation of number of car owned in households that will have 3 or more cars. So in this question, we have n number of trials equal to 400, okay, and we have the probability of success. The probability of owning 3 or more cars is 35% p. Okay. The question asks you, what is the mean of binomial distribution? Mean equal to n times p, n 400, p 35%. So that is the mean value. Okay. So how do you interpret this mean value? So in average, the household will have 3 or more cars, is 140. Okay. Now calculate the standard deviation of binomial distribution. Use this formula, n equal to 400, p equal to 0.35, and you get this number. Next is about the graph. How do you graph binomial probability distributions? Okay. Question A, graph the binomial probability distribution with n equal to h and p equal to 0.15. B, graph the binomial probability distribution with n equal to h and p equal to 0.5. As you can see, p increase. P represents the probability of success. Number C, graph the binomial probability distribution with n equal to h and p equal to 0.85. Oops. So let's see the first one. When n equal to h, p equal to 0.15, what you need to do, you need to calculate you need to calculate this one here. We need to have x and px. So when x equal to 0, what is the probability? You need to calculate this. How do you calculate? Use this formula here, the binomial formula. This one here, okay? Use binomial formula to calculate. When x equal to 0, okay, what is the px? Okay. Similarly, when x equal to 1, what is px? When x equal to 2, what is px? And 3, 4, 5, okay, etc. You'll see the probability decreased here, okay? And then you draw the histogram. Once you have this data, you can use Excel to draw the histogram. So this is a similar, n equal to 8, p equal to 0.15. Change the p value. When you change the probability value, you get this picture. Again, how did you get this? You need to figure out what is x, and then calculate px. Okay. And then you draw the histogram. And this one is the probability 0.85. So again, you select variable x, then probability of px, and you get this histogram. As you can see, if you have a smaller probability, the graph skewed to the right. If the probability is 50%, you have the bell-shaped symmetry. If the p is greater than 50%, you have skewed to left. Okay. So this is another example about the graph, the binomial probability distribution with n equal to 25, p equal to 0.8, comment on the shape of the distribution. Okay. If you can get from here, it is skewed to left. See, skewed to left, this graph. Okay. And this one, this example, when you have a large sample size, this is 50. This one, you only have 25. And then when you have a p, the same probability, 0.8. And if you graph the binomial probability distribution, you get roughly bell-shaped symmetry. This means when you increase sample size, it becomes bell-shaped symmetry. And this one, when you increase to sample size to 70, okay, see, almost bell-shaped symmetry. So this is the some statements. For a fixed p probability, the number of trials in binomial experiment increases. The probability distribution of random variable becomes bell-shaped. When you increase sample size, it is bell-shaped. It is close to bell-shaped. Okay. As a rule of thumb, if n times p times 1 minus p greater or equal to 10, the probability distribution will be roughly bell-shaped. Okay. So next, we are going to use empirical rule to identify unusual observations in a binomial experiment. Remember, the empirical rule said that in a bell-shaped distribution, 95% of all observations within 2 standard deviations of the mean. So 95% of the observation will be between mu minus 2 sigma, mu plus 2 sigma. Mu is population mean, sigma population standard deviation. Okay. Any observation that lies outside this interval will be considered unusual because the observation occurs less than 5% of the time. So let's look at an example, okay? A similar situation, automobile example. According to exploring automotive 35% of all car-owning households have 3 or more cars. A researcher believes this percentage is higher than the percentage reported by Experian Automotive. He conducted a simple random sample of 400 car-owning households and found that 162 had 3 or more cars. Is this result unusual? So that is the question. To answer if the result is unusual or not, we need to calculate the mean, standard deviation, and then we need to use empirical rule. So the mean of the binomial distribution, n times p. N is number of trials. P is percentage of success. So this is p, 35%, and this is n. Okay. And we also need to calculate standard deviation. NP times 1 minus p, take square root. And then we do mu minus 2 times standard deviation, mu plus 2 times 2 standard deviation, and we get these two numbers. So the usual number should be between 120.9 to 159.1. Okay, the given number here, 162. Okay, so 162 is outside the upper limit. Okay, so that's why the result is unusual. The result is unusual. Okay. All right. So in summary, what we did in this video, we did binomial probability distribution. First, we state the conditions or requirements for binomial probability distribution. And then we calculated the probability of a random variable, that is a binomial distribution. And then we give you the binomial distribution formula. We also graph binomial distribution. Okay, finally, we identified the unusual numbers in binomial distribution. That's all for this video. Thank you so much for watching. I look forward to see you in next lecture, Poisson distribution.